Alright, 3.2 logarithm functions. It's really just the inverse of an exponential. They all basically flip from one to the other. You still have a base that is greater than 1, or that is positive, excuse me, and then where your x value also has to be positive. So if you have y equal to log base of x, it's going to be equivalent to the base to the y power equal to x. Basically, it's the base, so it's going to be the base of your exponent. So the x goes to the other side, and then the y, switch that. The x is going to come to the other side, the y is then going to be your exponent there. So then it fits here. So again, whenever it's in log form, whatever's equal to, just another way of writing it, the y becomes your exponent, and then everything becomes equal to x. Okay, the x and the y basically flip sides, and you go from there. So a couple examples. Write the equation in exponential form. So if you start as a log, the only way you can go is to an exponential. So if I have log base 5, so again I'm going to send the x over here, so it's going to be x equals, the base doesn't change sides, so it's still 5, the 2 comes over, so 5 squared, x is equal to 25. Same way, 3's going here, 64 is going there. So 64 is equal to b to the third power. So you've got to figure out what number to the third power. If you need to, you can do the cube root. So what number times itself gives you 64. So 4 is equal to b. Same way, last one, the y is going to be your exponent, and then so I have 3 to the y power equals 7. Okay, so we would have to figure out what number to, so if that was in exponential form, that's how we would go about it. This one we'd pretty much have to stop because we don't know what that value is. Same way, going back the other direction, here is my base. So again, I'm going to write log base 12. I'm going to send the 2 over to the other side, the x over, so it's going to be x and 2. Same way, there's my base, so log base b, 8's coming to the other side, 3's going to the other, 8's a big, and there is 3. Last one. Now, this is e. I'm going to treat this as the natural log of e. So if you have log base e, 9's over, y and the 9 trade places, so there's 9 and then equal to y. If you ever have log base e, that is the natural, remember e is the natural number, so you're going to have the natural log of 9 equal to y. Okay. Anytime you have log base e, it's just going to turn into the natural log. When we get into it later, finding inverses, things like that, we can basically take the natural log and turn it into log base e. So then when we evaluate, all we're trying to do, if we just make everything equal to x, we're trying to figure out, so there's my base, 2 to what power equals 16. So if you know 2 to the 4th is equal to 16, so my value, log base 2 of 16, x is equal to 4. Same way, there's my base, we can make it equal to x, so 7 to the x power equals 1 over 49. Now, it's a fraction, so that means it has to be negative. So my x value has to be negative. Remember, 7 squared is 49. So then it's going to be 7 to the negative 2 power is going to give me 1 over 49. So my x value, or my exponent, has to be a negative 2. Here, log base 25 of 5, so 25 to the x power is equal to 5. So now if you go from a base to a smaller number, okay, and it's not a smaller, it's still a number bigger than 1, then what you want to do, then what's going to happen is it's going to be a fraction. So like here, where it was back on B, it went from a number between 0 and 1, so that's going to make it negative. Okay, that's just going to flip everything underneath. So in this case, remember, 25 is the square root of 25 is 5. So we can't write it as x equal to the square root. Okay? Anytime you have like a square root of something, that's to the 1/2 power. Okay? So I'm going to take 25 to the 1/2 power, and that's what's equal to 5. So x is equal to 1/2. Last one, if we have a fraction, or excuse me, a square root. So now this is to the 5th root. So basically what this is saying that we have log base 2 to the 2 to the 1/5 power. Okay. So whenever we have, and we'll talk about this later, especially this one's kind of a special case, when you have two bases that are the same, it's just going to be equal to my exponent. So it's just going to be 1/5. So just a few basic properties, really pretty self-explanatory. If it's log base b of b and there's nothing there, it's equal to 1. Okay? So just kind of like we talked about, if you have the same base, then it's whatever your exponent is. So if it would be b squared, then your answer would be equal to 2. If it was b to the 1/3, then it would be equal to 1/3. Okay? If your basis of your exponent and your of value is the same as your base, then it's just equal to whatever power that is. Vice versa, if it's log base b of 1, then it's always going to be equal to 0. Because anything to the 0 power, we know, is 1. The inverse properties, again, we've said it before, I've said it now 2 or 3 times, that if these two values match, then it's just equal to whatever my power. Same way, if I take b to the log base b of x, again, the base of my log, the base of my exponent are the same. It's whatever my of value is, or in some cases, my power in terms of how it's raised to it. So if we have log base 7 of 7, then that's just to the 1st power. So these two match, so it's equal to 1. Same way here. 5 to what power gives me 1? Well, it's going to be 0. Okay, if you can think about it as 5 to the x power equals 1, okay, then it has to be 5 to the 0 power. Same way, bases are the same, so the only thing left is equal to 5, or if you just want to call it x equals 5. And then the last one, base here, they just cancel. It's equal to 9. Now I'm going to go ahead and talk about graphing, so then if you just feel like you need something else to do along with whenever we graph a logarithmic function, so it's the inverse of an exponential. So remember, whenever we had an exponential, we had 4 things that we had to find. We had to find the y-intercept, the asymptote, and domain and range. Okay, so whenever we were doing these, whenever we were doing the one in red, we had the y-intercept, we had the asymptote, we had the domain, and then we had the range. Remember, with an exponential, domain was always negative infinity, positive infinity. Asymptote was whatever was plus or minus, so it would have been an asymptote of y equal to k, which in this case was 0. Our y-intercept, we just plugged in 0 for x, so we got y equal to 2 to the 0 power, so we got y equal to 1. Then our range, since it's above the so we would have, originally we had here, we had a y-intercept of 1, so it was above the line, so that meant my range was from 0 to positive infinity. And then we could plug in other points. 2 to the first power would be at 2, 2 to the second power would be at 4, if we need to go 2 to the third we could go to 8, and then basically look something like this here. Now, whenever we do a logarithmic function, instead of finding the x-intercept, we're going to find instead of finding the y-intercept, we're finding the x-intercept. Whenever we deal with our asymptote, instead of it being y equals, it's going to be x equals. Whenever we find our domain still, and then we find our range. Now, the opposite of these two, before domain was negative infinity to positive infinity, that is going to switch to our range. Okay. Our asymptote, so whenever we do this, we have log base b, we have an a out in front, log base b of x minus h plus k. So before we always looked at our k, now we look at our h. So it's going to be the opposite of h. So whenever it's x minus h inside, so we're going to set whatever we have equal to 0 for my asymptote. So in this case, I don't have an x minus h, so it's just going to be an asymptote at 0. So that just means that I'm going to have a vertical line here, and it's going to look something like that. Now, domain is all dependent, is it on the left side, is it on the right side? So if it's on the right side, it's going to go from your asymptote to positive infinity. If it's on the left side, it's going to go from negative infinity to that value. So whenever we do our x-intercept, okay, before we plugged the 0 in for x, now we're going to plug 0 in for y, okay, and solve it. This is going to be the hardest part of anything, and it's really not too bad. So I'm going to have 0 equals log base 2 of x. So remember, the x is going to go to the other side, the 0 is going to go to the other side, so I have x equal to 2 to the 0 power. Remember, anything to the 0 power is just 1, so I'm going to have a point here at 1. It's a reflection basically over this line, okay, since they're inverses of each other. So if what's going to happen is it's going to basically go right up along here and then turn this way. Okay, so it's like if there's my line of my reflection line, okay, since they're inverses of each other, that just means that they could reflect over y equal to x. Okay, the purple one and the red one are going to match each other. Okay, 1, 1, 0, 0, 1. If I went 2, I'd go up to 2, or excuse me, over to 2, up 1, so on and so forth. Okay? They're all going to be opposites of each other. Last part, and I should have done this before I drew the graph, since my x-intercept is on the right side, then I'm going to go from 0 to positive infinity. If you need to see any of the table, you can just look on the completed set of notes that are on the module. That's going to be no different. Last thing, so your domain is all dependent on what your, remember, it's going to be your asymptote is the opposite of whatever that value is. So you're going to set x plus 3 equal to 0. So if my asymptote is at -3, okay, it's positive. There's no negative anywhere. So like in this case, it's going to go from -3 to positive infinity.
Costco's like, it's the same thing as Sam Woods.